Welcome to the second part of our lecture on section 1.2 mappings. Again, we are using the text Elements of Modern Algebra 8th edition by Gilbert and Gilbert. We would continue our lecture from subsection 1.2.5 onto all surjective mappings. Let F be a mapping from A to B, where A and B are non-empty sets. We would assume in this class in general that if we define a mapping from A to B, then A and B are non-empty unless otherwise stated. We say that F is onto or surjective if B equals F of A. Interesting. Remember, B is the domain and F of A is the image of the entire set A, or the range of the function. So if the codomain equals the range of the function, then we say that F is onto or F is surjective. Alternatively, an onto mapping F is called a mapping from A onto B. Let us break that concept down a little so we can understand it better. I.e., what does that mean? If F from A to B is a mapping, again, where A and B are non-empty sets, then we say that F is onto or surjective if for every B in B, there exists an A in A such that B equals F of A. Basically, what we are saying is if I pick an element at random, an arbitrary element from B, I can always find an element from A such that A is mapped onto that element from B. There are a couple of things playing on around here, and let's check out what those things are. How do we apply this concept in proofs? Let F be a mapping from A to B, A and B non-empty. To verify that F is onto or surjective, these are the things we have to do. Preliminary step. You pick an element B in B. It has to be arbitrary. Then we do three things. We find A that has to sit in the set A and must fulfill the condition that B equals F of A. Three different things that we must verify before we can conclude that F is onto. Now, the order that I use personally is B equals F of A, find A, verify that the A I just found is actually from the domain. Once you pick an element B in B, you have to accomplish the three things that we have just mentioned above. And let us use an example to demonstrate this concept. Let F be a mapping from Z to Z. Z is the set of integers, so the domain is the set of integers and the codomain is the set of integers. Define F to be the function f of x equals 2x plus 5. Is F onto? Is F a surjective mapping? Well, let's check it out. Solution. Pick an element y in Z, where this Z here is your codomain, that is your B. Suppose y equals f of x. Remember the three things we have to show? So the first one is basically stated, not saying that it has happened, but we're saying suppose it actually were the case, would things work out for us? So Suppose y equals f of x. That is 1. Now, what does that mean? It means y equals 2x plus 5 because f of x is defined as 2x plus 5. I solve for x. Remember, find a. That's the second thing. So I solve for x and I get x equals y minus 5 divided by 2. That is my second point. So I have accomplished 1. I have accomplished 2. Believe it or not, the step that determines whether f is onto or not is actually step 3. You can always suppose that b equals f of a. You can always solve for a. It doesn't matter how complex the equation is, you can always factor out a. So the question is, does that a actually reside in the domain? And in this case, our domain is z. So we have x equals y minus 5 over 2. So that is our x. We just found it. And the last part is, does this x reside in the domain which is z? For every y, it has to hold for every y. Well, why don't we take y equals 6? Then x becomes 1/2, which is not an element in z. That is not an integer. Step 3 fails, and therefore f is not onto. It is not surjective. Observe that if I change my domain from the set of integers to the set of real numbers, my function is surjective. The domain and the codomain are very important when verifying that functions are onto. Okay, let's go ahead and define what it means for a function to be injective or one-to-one. Let f be a function from a to b, a and b non-empty. Then f is said to be one-to-one or injective if and only if different elements of a always have different images under f. Now let's break that down very quickly so we can understand it even better. So what we are saying is, if f is a mapping from a to b, a and b non-empty, then f is said to be one-to-one or injective if and only if for every x1, x2 in a, whenever f of x1 equals f of x2, x1 must be equal to x2. This is the core. This is what you verify when you're proving that f is one-to-one. Or in the contrapositive, you can prove that whenever x1 is different from x2, f of x1 has to be different from f of x2. But this would be the favorite right here. Let's start with a little problem. Define the function f from the set of integers to the set of integers by f of x equals 2x plus 5. The same function we saw above that was not onto. Is f one-to-one? Is it injective? How do we verify that f is injective? We pick two elements, x1 and x2 in z, arbitrarily, and we suppose that f of x1 equals f of x2, and logically show that x1 equals x2 without cheating. So we start. Suppose x1 and x2 are in z and f of x1 equals f of x2. We show that x1 equals x2. But f of x1 equals f of x2. What does that mean? It means that 2x1 plus 5 equals 2x2 plus 5 because of the definition of f. Add -5 on both sides. that is the additive inverse of 5, we have 2x1 equals to x2. And if I pull my 2x2 to the left and factorize out 2, I end up with 2 into x1 minus x2 equals 0. 2 is different from 0, so x minus 1 must be equal to 0. Now, x minus 1 equals 0 implies that x1 equals x2, and we have just verified that f is 1-to-1. End of proof. Very easy. That is how we prove that f is 1-to-1. And before now, we saw how to prove that f is onto. Now, if f is both 1-to-1 and onto, those kind of functions have a special name. Subsection 1.2.7, one-to-one correspondence bijection. If f is a mapping from A to B, A and B non-empty, then the mapping F is said to be bijective if and only if it is both surjective and injective. It is 1-to-1 and it is onto. So the function we just saw in the last example was not bijective because it was 1-to-1, but it was not onto. Look at problem number 1. Define the function f such that the domain is a set of real numbers except the point 0, and the codomain is a set of real numbers by f of x equals 2x minus 1 divided by x. Observe that this function is well defined because 0 has been excluded, so the fear of dividing by 0 is not there. Question: is f a bijection? Can you verify that f is onto? Again, what do? We pick an element y in a set of real numbers. We find an element x from the domain such that y equals f of x. Is f 1-to-1? Again, what do? Suppose x1 and x2 are from the domain and are arbitrary, and f of x1 equals f of x2. That means 2x1 minus 1 divided by x1 equals 2x2 minus 1 divided by x2. Can I logically, without cheating, prove that x1 equals x2 just using simple equal signs? If that is the case, then f is a bijection. Otherwise, it is not. Look at the second example. Even more exciting. Let f be a mapping from the set of integers to the set of integers. The domain is a set of integers, and the codomain is the set of integers. And f is defined as follows. F of x equals 2x minus 1 when x is even, and f of x equals 2x when x is odd. Is f onto? Is f 1-to-1? Can we say f is a bijection? Interesting questions. Solution. I would leave these as simple exercises for serious students. Play with this, and we may look at it in class for those who are taking the class with me right now. Subsection 1.2.8 Composite Mapping. Let G be a mapping from A to B and F be a mapping from B to C. What do you see here? G goes from A to B, F goes from B to C. Now let's use a non-mathematical language and say that G feeds from A and F feeds from B. The domain of G is A. The codomain of G is B, whereas for F, the domain of F is B and the codomain is C. If this happens, then we can actually define a composite mapping F composed with G as a mapping from A to C. Now let's look at the picture below. A, B, C. F is a mapping from B to C. G is a mapping from A to B. I have a mapping from A right over to C, and we call this F composed with G. G feeds on A, takes the elements to B, those are the images, and F feeds on those images, and its images would be in C. So we define the composite mapping as F composed with G of X equals F of G of X. So you can see G feeding on X, F feeding on G of X, and that happens for every X in A. Now observe that X is an element in A and G of X is an element in B. We shall prove some exciting properties of composite mappings in section 1.3. That will be the next lecture after this. But we would not go without giving you at least one example from composite mappings. Problem number 1. Let F be a mapping from Z to Z, the set of integers, and G also a mapping from Z to Z, so that's very good. Define those mappings as F of X equals 2X and G of X equals X cubed plus 2X. I want you to find F composed with G of X and hence compute F composed with G of negative 3. F composed with G of X by definition equals F of G of X, which equals F of, this is how we define G of X, X cubed plus 2X, which equals, we take all of this and substitute it for X in the definition of F of X. So that gives us 2 into X cubed plus 2X, and we can distribute that to have 2X cubed plus 4X. Therefore, F composed with G of negative 3, your negative 3 is your X. That equals 2 into negative 3 cubed plus 4 into negative 3, and your final answer is left as a simple exercise for serious students. Problem number 2. Once more, let F be a mapping from Z to Z and G a mapping from Z onto Z. Define both mappings as follows. F of X equals X over 2 if X is even, or X plus 1 if X is odd. Now observe that this is defined properly. If X is an even number, then X would have to be in the form 2K. The 2's will cancel out and leave you with an integer because the domain has to be an integer and the codomain an integer. Define G as X minus 1 if X is even and as 2X if X is odd. Now I want you to find for me the composite map F composed with G. Interesting. Play with that some and let's see what you would come up with. And for the students who are taking this class with me right now, I will check and see in class what you did with this problem. So that is left as a simple exercise for serious students. And this brings us to the end of the second part of section 1.2 mappings. And watch out for the release of section 1.3, some properties of composite mappings. Thank you and God bless you.